Welcome to week 2 of network analysis ELE 311T. In the last week, we saw differential equations and their utilization in solving networks. We saw that we'll be mostly dealing with ordinary differential equations with constant coefficients. And these ordinary differential equations would be linear by nature because the circuits that we are talking about are linear by nature. And constant coefficients makes them time invariant. So this is possibly the simplest case within the framework of differential equations, and this is useful in solving quite a number of circuits. We saw in the last week that ODEs can be solved using standard methods in mathematics. You can have homogeneous ODEs wherein the forcing function is zero, identically zero. And we can have non-homogeneous ODEs wherein the forcing function would not be zero. And we saw how to solve both homogeneous ODEs and non-homogeneous ODEs for a set of forcing functions which is commonly encountered in network analysis. So we are well equipped now with the basic tools of mathematics to begin our analysis part within the networks. Now this is going to take us most part of this week. We're going to basically see how to use differential equations to solve networks. So what is the framework in which we are operating? We have already seen that for DC circuit analysis, we have tools like Kirchhoff's current law, Kirchhoff's voltage law to give us basically what we are solving for is the steady state DC voltage or current parameter. So then we saw in the first semester that we can get more sophisticated tools out of KCL and KVL, and those are given by, like for example, mesh analysis and nodal analysis, wherein we can deal with circuits which are more complicated, which are bigger in size, but we're basically working only to get the steady state DC voltage or current parameter, in the sense that we are given a big circuit and we are told that we want a particular current or a particular voltage. Now we in this course, we're not just interested in getting a particular DC steady state voltage or current parameter. We are basically interested in finding the transient behavior of the system as well. So we are basically interested in completely characterizing the time domain behavior of a network. This actually means that uh, we are basically, like for example, if you have a circuit which we saw on the last turn, we have a resistor and we have an inductor, and we saw that the current response of this circuit is going to be something like this. It's going to have a steady state value, which is V by R, wherein V is the voltage, R is the resistance, L is the inductance. But it's not going to rise to V by R instantaneously because of the inductor. The current response is going to be something like this. So there is a transient period in the response, and there is a steady state period in the response. So what we have done till now in simple DC circuit analysis is we have found out the steady state behavior of this circuit. So we were basically doing analyzing the circuit only for the steady state response. Now we are also interested in this part of the course to find out the transient response of the system. So we want the complete time domain characterization of the network. The tools that we use are tools that we take from basic circuit theory, KVL and KCL, and the tools of differential equations that we have studied in mathematics in the first semester, and then we revised a little bit this semester. So we'll be using the tools that we have already seen. We are using KVL, KCL, or their modified versions like mesh analysis and nodal analysis. And then we'll be using our knowledge of differential equations to, to reach to our objective, which is characterizing the time domain, characterizing the complete time domain behavior of the network, finding the complete time domain behavior of the network. So for this, we have to first we have to first write the differential equations, which we write using these methods, and then we solve the differential equations. The general format of the problems is going to be like this. We'll be given a network connected to some excitation through a switch, and we'd be told that the switch is closed at some particular time, t is equal to 0 for example, and we'd be asked to find the particular response which is given by xt, which may be a current or a voltage in the circuit. So a network is given and a response is required, wherein the network is connected to an excitation at a particular time. So normally the initial conditions that we encounter in this case are available at t is equal to 0 minus, that is to say at the instant just before switching, and to find the response xt we need the initial conditions at t is equal to 0 plus, that is to say just after switching, because we have already seen that to solve differential equations we need the initial conditions at t is equal to 0 plus. So one important part of the problem would be to find the initial conditions. To find the initial conditions. At t is equal to 0 plus, where 0 is generally taken as the time of switching. The other important thing is that we should remember that we are talking about linear circuits. So the principle of superposition is valid. The advantage is that we can take one excitation at a time, see the response, and then add all the responses to all the excitations at the end. So throughout this course, we'll be talking only about linear circuits. That's why we have linear ODs modeling the circuit. And we have to remember that we're talking about superposition principle remaining valid throughout. So if you have a network with multiple excitations, that's not a problem. We can take one excitation at a time, find out the responses due to different excitations, and then simply add the responses to get the final response of the circuit. So before we start actually solving some problems, we first see this problem of initial conditions and how to resolve it in the framework that we're talking about. So finding, this is the first topic, initial conditions at t is equal to 0 plus. Remember that we are talking about networks which have elements resistor, inductor and capacitor. And because of the peculiar characteristics of inductor and capacitor, we can write down the initial conditions at t is equal to 0 plus, that is just after switching, where 0 is the switching instant. From our knowledge of the initial conditions, at t is equal to 0 minus, that is just before switching. And how is that? Let us take the example of the inductor. We know that the governing equation for the inductor is Vt is equal to L dit by dt, where It is the current through the inductor and Vt is labeled like this. Now let us suppose that this inductor is connected to a switch which is connected to a voltage source and we want to see what is happening actually in the circuit. So this is the voltage source, let us say it's capital V. In this circuit, Suppose this voltage source V is a constant DC source, which is also evident from the notation capital V. And suppose that the current at 0 minus, when the switch is closed at 0, is 0. So do we know the current at 0 plus? Yes, we do. And how do we know it? We know that I0 plus in this case is going to be equal to I0 minus, because the current in the inductor cannot change instantaneously. Why can it not change instantaneously? It cannot change instantaneously because an instantaneous change in current would require an infinite amount of voltage to be applied. And that is clear from the equation. Instantaneous means change in zero time. So this dt is 0 and this is finite because there is some change. So it is some finite quantity divided by 0, which is infinite. And what does it mean? It means that an infinite amount of voltage has to be applied. And basically, inductor is defined as the property of the circuit which resists the change in current. It is a property of the circuit which resists a change in current. So if you want the current to change instantaneously in the inductor, you have to apply a forcing function which is infinite in nature, which is not in this case because this is a constant DC source. It's going to be something like this. There is no voltage at t is equal to 0, and at t is equal to 0 you start applying a voltage V. This is the profile of the voltage applied to the circuit. So from the from the property of the inductor, it is clear that I0 minus has to be equal to I0 plus, because the excitation does not contain an impulse or any derivative of the impulse. That's how we write it. Because the excitation does not have anything going up to infinity, or because derivatives of impulses are also quantities that rise up to infinity. So because the forcing function does not contain an impulse or any derivative of the impulse, it's a simple constant DC voltage source, it is very clear that the voltage at 0 minus is the current at 0 minus through the inductor is going to be the current at 0 plus. Similar arguments can be made for the capacitor also. In the capacitor also, we know that IT is equal to C dVt by dt. So an instantaneous change in voltage, of the capacitor, instantaneous change is possible only if infinite current flows through the capacitor. Which in most of the real cases or practical cases is not possible. We don't have impulse sources existing in reality. So it is practically impossible to force a capacitor to change its voltage instantaneously. That is why in all the cases in which the sources don't contain impulses or derivatives of impulses, will be following this general principle that the inductor current is not going to change instantaneously and the capacitor voltage is not going to change instantaneously. That is, the current before switching in the inductor is going to be equal to the current after switching in the inductor, and the voltage before switching in the capacitor is going to be equal to voltage after switching in the capacitor. This thing is also clear if we look at the derivative form of the equation, which I'll show for the capacitor and which can be extended or written similarly for the inductor. For the capacitor, we have written the derivative for on the integral form of the equation as VCT is equal to VCT1 plus 1 by C integral T1 to T IT dt. Now suppose we're talking about T1 being equal to 0 minus, and the instant in which we are interested to find out the voltage of the capacitor is the instant 0 plus. So we can write the above equation as the voltage of the capacitor at 0 plus is going to be the voltage of the capacitor at 0 minus plus 1 by C integral all the currents that have been applied from 0 minus to 0 plus on the capacitor. So this integral that we're saying here is integral of all the currents that have been applied from in this time 0 minus to 0 plus, and it is 0 for all IT except ones containing impulses, because we know that the integral of the impulse function del t is 1, del t dt is 1 from 0 minus to 0 plus, or from minus infinity to infinity, because it exists only at 0. So this integral is going to be non-zero only if it has impulse or it has a derivative of the impulse, which is not possible in the normal case, which is not something that we generally encounter. That is why in most of the cases Vc0 plus is going to be equal to Vc0 minus. A similar derivation can be seen for the inductor also. So to summarize, what we're going to do now mostly is write the differential equations. 3 steps basically. Number one, we are going to write the differential equations, the ODEs governing the network by standard methods in electrical engineering like mesh and nodal analysis. Then the next step is we're going to find the initial conditions, which are conditions at 0 plus, conditions at t is equal to 0 plus, by applying the properties of the inductor and the capacitor, which are that the inductor In the inductor, the current does not change instantaneously, and in the capacitor, the voltage does not change instantaneously if the source does not contain impulse or its derivative. And a third part would be we'll solve the network differential equation that we have obtained using methods that we have seen in week 1. And which was the method of undetermined coefficients. So this is what the next lecture is going to be all about. We're going to start solving equations to characterize the complete time domain behavior of the system.